and how Android handles USB connections, it could potentially gain access when plugged in.
The book introduces fuzzing here as a way to find vulnerabilities. Quick explanation.
Fuzzing is basically throwing tons of garbage data at a program to see if it breaks.
Just random stuff.
Sometimes random, dumb fuzzing. Sometimes slightly modified valid data, smart fuzzing. You feed it massive amounts of unexpected or malformed input and watch for crashes or weird behavior. Those often point to bugs, potentially exploitable ones.
Can you fuzz Android easily?
There are challenges keeping the system stable, performance limits on phones, but yes, it's done. The book gives an example of fuzzing Chrome for Android by feeding it weird JavaScript typed arrays, which found real vulnerabilities. Okay, let's say fuzzing finds a crash, or you suspect a flaw. Debugging and vulnerability analysis. How do you figure out what's actually going on?
First step, the book says, is gather all the info you can. What does that mean?
Everything relevant, documentation, the source code if possible, like for AOSP, the actual compiled binaries, any symbol files.
Symbols.
Yeah, they map the machine code back to human-readable function and variable names. Super important. And of course, the right tools for analysis. Getting the full picture is key.
Why are symbols extra important on ARM, the processors in most phones?
Symbols bridge that gap between raw binary and source code. On ARM, the instruction set and debugging can be a bit more complex than, say, by86 on a PC. Good symbols make tracing execution, understanding what function is calling what, and finding the root cause much easier. Without them, you're just staring at numbers.
The book lists essential tools: Eclipse, Android, SDK, NDK, ADT plugin. What does it do?
Eclipse with the ADT plugin was a common integrated development environment, IDE, for writing, building, debugging Android apps. The SDK, Software Development Kit, have the core libraries and tools. The NDK native development kit lets you write parts of your app in CC++, not just Java Kotlin. They're the basic toolkit.
Setting up a proper debug environment sounds key. Attaching source code, debugging on a rooted device.
Yeah, you need to be able to step through the code, see variable values. Eclipse, or modern tools like Android Studio, lets you link the Android framework source code so you can see what it's doing when your app calls it.
And rooting helps.
Rooting gives you higher privileges, essential for debugging system processes that normal apps can't touch. The book mentions an app, rootadb, that helps enable full debugging on rooted phones.
What about debugging the native CC plus parts, different tools?
Usually involves GDB, the GNU debugger. The NDK includes NDK-GDB. You can run a GDB server on the phone and connect remotely from your computer, often integrated into your IDE like Eclipse or Android Studio. The book walks through setting that up.
The book notes that production phones often have fewer symbols. Why?
To save space. When they build the final release software, they often strip out a lot of the debugging symbol information to make the files smaller.
Makes debugging harder, though.
Much harder. You lose function names, variable names. Engineering builds usually keep more symbols. The book gives tips for working with limited symbols, maybe even generating your own if you have the source.
What's dynamic binary instrument DBI, an alternative to debuggers?
Kind of.
Yeah.
DBI tools let you inject your own code into a running process more dynamically without constantly stopping it like a traditional debugger.
What's it good for?
Less intrusive analysis, tracing function calls, watching memory access, collecting performance data without the start-stop overhead. Good for understanding complex behavior in real time.
When something crashes, finding the root cause is crucial. What is that exactly?
It's the fundamental reason for the crash, not just the symptom, app close, but the underlying bug memory corruption, a logic error, bad input handling. You need the root cause to fix it properly and understand the security risk.
The book walks through debugging a Chrome crash related to typed arrays, setting breakpoints, checking registers, looking at source code. What's the main lesson there?
It really shows the methodical process. You take the crash dump info register values, the stack trace, which functions were called, and use that to find the exact failing instruction.
And then you look at the code.
Right. You examine the source around that instruction, maybe use memory analysis tools like those for Dillamalik to figure out the sequence of events. In that case, it led to a use-after-free bug using memory after it was supposedly returned to the system. It highlights needing to dig deep, combine crash data with code understanding to find the why. Okay, let's get into exploiting user space software. Memory corruption basics. What are the main targets?
The book mentions two key memory areas, the stack and the heap. Can you simplify what these are and why corrupting them is bad?
Sure. Imagine the stack like a stack of plates for function calls. When a function starts, a new plate goes on top with its local variables and, importantly, the address to return to when it's done. A stack buffer overflow is when you write too much data onto that plate, spilling over onto the plate below. If you overwrite the return address on that lower plate with the address of your own malicious code.
You hijack the program when the function tries to return.
Exactly, you take control. The heap is different. It's more like a big shared storage locker where programs request chunks of memory dynamically while they're running,
How do you exploit that?
often by corrupting the metadata the system uses to manage those chunks, like the size information or pointers linking free blocks. If you can mess with that metadata, you might trick the system into letting you write data anywhere you want, or maybe overwrite function pointers stored on the heap, like virtual function tables.
Virtual function tables.
Yeah, they tell an object how to behave. If you can corrupt the pointer to that table on the heap, you can make the object run your code instead of its own methods when called.
The book mentions specific memory allocators. Android's Dialog and WebKit's Render Arena. Any significance there?
Dolmalloc is the standard allocator used in many Android native libraries. It has somewhat complex metadata mixed in with the allocated memory. WebKit, the browser engine, uses Render Arena for some objects. It's simpler, faster, and has less metadata inside the memory blocks themselves.
Does that make it easier or harder to exploit?
Potentially different techniques apply. Maybe the simpler Render Arena metadata is easier to overwrite without triggering internal checks, for example. The design affects the exploit strategy.
Let's revisit those earlier exploits. Gingerbreak, Zergrush, Mempodroid. What memory corruption techniques did they use?
Okay, Gingerbreak, as we said, used an array indexing bug to overwrite the global offset table GOT, corrupting function pointers. Zergrush used ROP, which isn't direct memory corruption for code execution, but manipulates the stack to control execution flow using existing code. Mempodroid was a kernel bug allowing writes to arbitrary memory in other processes, direct, powerful memory corruption.
The book analyzes a specific Android browser WebKit exploit. How did that one work in terms of memory corruption?
That exploit focused on controlling the heap. It involved carefully allocating and freeing specific WebKit objects, render blocks, to manipulate the heap layout.
To what end?
The goal was to overwrite the virtual function table pointer of one of these objects. By controlling the heap layout, the attacker could place their desired fake function pointer address where the object's real pointer should be.
So when the browser used the object,
Bam! It followed the corrupted pointer and jumped to the attacker's code running within the browser's process. Classic heap exploitation. Gain control of an object's behavior by corrupting its function pointers via heap manipulation. Okay, let's properly dive into return-oriented programming, ROP. Fascinating stuff. Why did this technique even emerge?
ROP sounds complex.
Yep.
The book says it was largely a response to that execute never XN or NX mitigation. Remind us what XN does and how ROP gets around it.
Right. XN is that hardware feature stopping code execution from data areas like the stack and heap, a big hurdle for attackers who used to just inject their code there and run it.
So how does ROP work?
ROP's clever insight is, okay, we can't run code from the stack, but there's tons of existing legitimate executable code already in the program's code sections and libraries. ROP finds tiny snippets of this existing code called gadgets that end with a return instruction. By carefully placing the addresses of these gadgets onto the stack, one after another, along with any data they need.
You chain them together.
Exactly. The return instruction at the end of one gadget pops the next gadget's address off the stack into the program counter, making the CPU jump to the next snippet. You basically build your desired functionality by stitching together little pieces of code that are already there.
Like Legos made of existing code.
That's a great analogy. You're not injecting new bricks, just rearranging the existing ones using the stack as your instruction sheet.
The book mentions ARM separate code and instruction caches. How does that relate to ROP?
That separation is key to how XN works. The CPU fetches instructions from the code cache and data from the data cache. XN tells it, don't execute anything fetched from a region marked as data.
But ROP gadgets are in code regions.
Precisely. ROP manipulates the stack data region to control the program counter, PC, making it jump to gadgets located in legitimate code regions. The CPU happily executes these because they're in executable memory. The final read in the gadget uses the stack data to find the next gadget address code. So ROP respects XM but still achieves arbitrary computation by redirecting control flow through existing code.
How do you even find useful gadgets?
Yeah.
Seems like searching for needles.
It can be, but there are tools, and often good gadgets come from predictable places. Compilers often generate standard little code sequences at the end of functions' epilogues to clean up the stack and return.
Ah, the cleanup code.
Yeah, these epilogues often pop values into registers and then do the final ret. Disassembling the program and looking for these short sequences ending in ret helps build a library of available gadgets. A successful ROP attack needs enough useful gadgets to string together.
What about the dynamic linker? The thing that loads libraries. How does it fit into ROP?
The linker resolves function names to actual memory addresses when a program loads. This matters because attackers often want their ROP chain to call useful library functions, like system, to run a command.
But ASLR randomizes library addresses.
Right. Address space layout randomization makes it hard to know where those library functions are. The book notes that in older Android, pre-4.1, the Bionic linker itself often loaded at a fixed address. Easy target.
But not anymore.
Newer Android uses ASLR for the linker too, so an attacker might first need an information leak vulnerability to find out where the linker or other key libraries got loaded in memory this time, before they can build a ROP chain that reliably calls functions inside them.
The book has a case study, ROP exploit on the Android 4.0.1 linker. What was the goal and how did it work?
The goal there was to execute arbitrary code from a new chunk of memory the attacker controlled. A key trick was stack pivoting, changing the stack pointer to point to a memory area controlled by the attacker, which contained their carefully crafted ROP chain. Then it used a neat trick involving how WebKit laid out strings and their data buffers next to each other in memory. They built a ROP chain using gadgets from the predictably located linker to call memcopy.
A memory copy function.
Yeah, to copy their actual malicious payload, shellcode, into a newly allocated executable memory region. The final step of the ROP chain was then to jump to that payload. Voila! Arbitrary code execution, really intricate stuff, shows the level of detail needed. Okay, deep breath, let's go deeper. Hacking the kernel, the core of the OS. Where do you even start with that?
First step, the book says, is getting the kernel source code. Where do you find that?
Main place is AOSP, the Android open source project. That has the base Linux kernel with Android patches.
But phones aren't just base Android.
Exactly. Manufacturers, OEMs, heavily modify the kernel for their specific hardware, so you often need to find the kernel source released by Samsung or Qualcomm or whoever made the specific device you're targeting.
How do you know you have the right version?
You need to match it to what's running on the phone. You can usually check perk version on the device or maybe unpack the kernel image file itself. Then you use Git to check out that exact code commit from the OEM's repository.
Okay, got the source. Now you need to build it.
Yep. You typically use the pre-built compiler tool chain from AOSP, the right GCC version and tools. Then you configure the kernel build, often starting from a def config file, which is like a template configuration for that device model.
Like the Galaxy Nexus example in the book.
Right. Then you run the build command, and it spits out a kernel image file.
How do you get that onto the phone?
You need to package it into a boot image that usually includes the kernel plus an initial RAM disk in ITER. Tools like mco booting from the Android build system do that.
Then flash it.
Yeah. For many OEM devices, you need their specific flashing tool. The book mentions Samsung's Odin, for example. You put the phone in a special download mode and flash your custom boot image onto the boot partition, assuming the bootloader allows it, of course.
Running your own kernel code sounds powerful. But what if it crashes? Debugging the kernel must be tricky.
It can be. First stop is the kernel crash logs, kernel panics, or oops messages. Check proc nsg, proclass kmsg, or maybe data.panic.
What does tell you?
Lots. CPU register values at the time of the crash, flags, memory contents nearby, the call stack leading to the error. Invaluable clues. You can also sometimes tweak settings to stop the phone rebooting instantly after a kernel panic, giving you time to grab the logs.
What about more interactive debugging? KGDB.
KGDB is the new kernel debugger. It lets you connect to a running or crashed kernel, set breakpoints, step through code, inspect data structures, much like debugging a normal program.
How do you set that up? Sounds complex.
It involves building your kernel with specific KGDB options enabled, config GDB serial. Then you usually need a physical serial connection to the device special cable, often required, and run GDB on your host machine connected to that serial port.
Any pitfalls?
Oh yeah. Watchdog timers might reset the phone if you pause it too long in the debugger. Screen blanking can interfere. Getting the serial connection working right can be fiddly, but it offers deep insight when you need it.
Android kernels are Linux, but they vary, right? Versions, manufacturer
But
changes.
certainly. You see older 2.6 kernels, lots of 3.x, newer 4.x kernels. Plus, all the custom drivers and modifications OEMs add for their specific hardware. But the core Linux parts, memory management, scheduler, networking, are largely consistent underneath.
The book uses the SOCDIAG bug as a case study, a Linux kernel bug affecting Android.
Yep, it was a use-after-free vulnerability in the kernel's network diagnostics code, triggered by sending a specific kind of netlink message.
Use after free, using memory after it's been released.
Exactly. Can lead to crashes or let an attacker overwrite that freed memory with their own data, potentially hijacking kernel execution. The exploit involved leaking kernel addresses, mapping user space memory cleverly, and taking control.
Did it work on all Android devices?
Mitigations like mapmanod, which prevents mapping memory at very low addresses, could make exploiting it harder on some devices. But it shows how a general Linux flaw can directly impact Android security, because Android is Linux at its core.
Okay, switching gears again. The radio interface layer RIL, talking to the cell network. Why attack that?
The RIL is described as an abstraction layer. What's it abstracting? Hiding.
It hides the messy details of different cellular radio hardware and network protocols, GSM, CDMA, LTE 5G, from the main Android OS and apps. It provides a consistent way for Android's telephony services to talk to the radio, whatever type it is.
Like a universal translator for cell signals.
Pretty much, yeah, between Android software and the radio hardware.
And phones have separate chips for Android apps and the radio, right? Application processor and baseband processor.
Usually, yes. The application processor runs Android. The baseband processor is a dedicated chip, often running its own proprietary real-time OS, just handling the radio communication. The RIL is the software bridge between them.
How does the RIL fit into the Android framework? It mainly provides an interface for the telephony manager service. It also defines common telephony concepts, so app developers don't need to worry about, say, the difference between a GSM signal strength and an LTE signal strength indicator. The actual low-level work is done by the RIL daemon, RILD, a native process.
How does that RIL talk to the baseband chip vendor role?
Exactly. Each device usually has a specific vendor shared library. This library knows the proprietary commands or standard protocols, like GSM AT commands, needed to communicate with that particular baseband chip from that particular vendor, Qualcomm, MediaTek, etc.
How do you know which one a phone uses?
The book suggests checking the init.rc boot script, which usually starts RILD and tells it which library to load, or looking at the libraries loaded by the running RILD process.
The book dives into the SMS PDU format. Why is that low-level detail important for RIL security?
PDU is the actual data structure of an SMS message. Fields for sender number, timestamp, the message text itself encoding info. If you want to fuzz or attack the RIL's SMS handling, you need to know the structure. You craft test messages with weird or invalid data in specific PDU fields to see if you can break the RIL's parser or cause other problems in the RIL or the baseband.
So how do you fuzz SMS on Android?
You generate lots of these crafted SMS PDUs. Then you need a way to inject them into the RIL. The book mentions a tool, Injectored, that can send raw PDUs to a fake serial port that RIL often listens on for testing.
Then you just watch for crashes.
Yep, monitor logs, logcat, kernel logs, watch for the RILD process crashing or the whole radio acting weirdly. If something breaks, you analyze the logs and try to figure out which malformed PDU caused it and why.
The book has Python code using Injectored. Seems quite hands-on.
It is. Understanding the protocol and having tools to inject raw data lets you probe the RIL at a level normal apps can't reach. You find bugs that normal usage would never trigger. Okay, last major topic. Exploit mitigations. All the defenses Android uses to make exploitation harder. There are quite a few.
Yeah, the book lists a bunch. Stack canaries. What do they do again?
They're like tripwires on the stack. A random value placed near the return address. If a buffer overflow overwrites it, the program detects it before returning, using the corrupted address, and usually just crashes safely instead of letting the attacker take control.
Address space layout randomization. ASLR, randomizing memory locations.
Exactly. Libraries, heap, stack, they get loaded at unpredictable addresses each time. Makes it much harder for attackers to know where their target code or data is located. Crucial mitigation. Android got full ASLR around version 4.0.
No execute NX or XN. We mentioned this with ROP. Stops code running from data areas.
Right. Marks stack and heap memory as non-executable, prevents simple code injection attacks, forced attackers towards techniques like ROP. Android supported it early, 1.5, but getting everything compiled properly took time.
Position independent executables, PIE, rel bind now. More randomization and protection.
PIE makes the main program executable itself, load at a random address, just like ASLR does for libraries. Or LRO, relocation read-only, and bind now protect the tables the linker uses to find functions. They make these tables read-only after setup, stopping attackers from corrupting them to redirect function calls.
Format string protection and fortify source. Compiler checks.
Yep. Format string bugs happen when print-like functions process user input directly. Compiler flags help catch these dangerous patterns. Fortify source adds runtime checks for things like buffer sizes during memory operations, trying to catch overflows as they happen.
So Linux, security enhanced Linux, how does that help?
So Linux is mandatory access control, MAC. It enforces much stricter rules about what processes can do and access beyond basic user permissions. Even if an attacker exploits one app, Linux policies aim to contain them, limiting the damage they can do to the rest of the system.
The book also mentions kernel hardening and specific Android version changes, like tighter logging and content provider defaults.
Yeah, ongoing efforts to make the Linux kernel itself more secure. And Android itself has evolved, blocking third-party apps from reading system logs easily, Android 4.1, making content providers private by default unless explicitly shared, Android 4.0, layering defenses.
There's even a table showing when these compiler defenses became default in the NDK. Shows progress.
Definitely a trend towards building security in earlier, but as the book says, attackers adapt. ROP bypasses NX, info leaks bypass ASLR, predictable kernel layouts weaken kernel ASLR.
So mitigations aren't foolproof.
Not at all. They raise the bar significantly, make exploits harder, more expensive, less reliable. But determined attackers often find ways around them. It's that constant arms race. Okay, final area. Hardware attacks. Need physical access for these. What opens up then?
Hardware attacks sound serious. Need the device in hand, but potentially gain deep access. What interfaces do researchers look at?
Common ones are UART, the serial console, often active on dev boards or prototypes. I2C and SPI buses used for chips to talk to each other on the board, sensors, memory, and JTAG, the standard for low-level debugging and programming chips directly.
What tools help with this? Multimeters, logic analyzers, JTagulator.
Multimeter for basic voltage continuity checks. Logic analyzers, like SALI, capture the digital signals on I2C, SPI, UART so you can see the raw data. JTagulator helps find the JTAG pin connections if they aren't documented. Bus Pirate is another handy tool for talking various serial protocols.
What kind of flaws might you find? The book mentions bootloaders accessible via UART.
Yeah, if you can get a command prompt on the bootloader, like uboot via UART, you might get powerful commands.
Yeah.
Read-write flash memory, network boot, firmware updates. A huge security hole if not protected. Lets you bypass OS security entirely.
Can you seal secrets or firmware this way? Observing buses, chip off.
Potentially. Watching I2CSPI might reveal crypto keys or config data being passed around. Chip off is more hardcore. Physically removing a flash memory chip, putting it in a reader, and dumping its entire contents gives you the full firmware for offline analysis.
Reverse engineering that firmware sounds tough. IDA Pro helps, but challenges remain.
Very challenging. IDA Pro disassembles the code, but figuring out function starts, data structures, ARM versus thumb instruction modes without symbols is hard work. Plus, hardware hacking is risky. You can easily brick the device or fry the debug interfaces if you're not careful. It takes time and patience.
Okay, we've covered a ton of ground from the Android Hacker's Handbook. What's the big takeaway for listeners?
Yeah, wow. It really boils down to the sheer complexity, doesn't it? Android security isn't just one thing.
Not at all. It's layered. From the high-level ecosystem and app permissions, down through user space exploits, ROP, kernel vulnerabilities, all the way to the radio and even the physical hardware.
And understanding those layers, how they connect, where the cracks might appear, that's key. Absolutely crucial to appreciate the challenges, the defenses, the constant push and pull. It's the whole picture, the interplay of all these parts that defines the security of your device.
So as you're processing all this, here's something to chew on. This Android security world is this constant battle, this arms race. Researchers and attackers finding holes, developers building walls.
We're always evolving.
And because Android is so open, so widespread, there are always new places to look, new ways to attack, and new ways to defend. How does knowing a bit more about this change how you think about the phone in your pocket?
Yeah, maybe it makes you think twice about that random app permission. Or connecting to unknown Wi-Fi.
Exactly. A deeper understanding hopefully empowers you, helps you make smarter choices. We've only scratched the surface here today, really.
Definitely. The handbook goes way deeper, and the field keeps moving fast. But hopefully this gives you a solid foundation to build on and maybe spark some curiosity to keep exploring this fascinating world of mobile security.